A single equation changed everything casinos thought they knew about randomness. Two physics students proved that the most unbeatable game in Las Vegas was actually just Newton's laws in disguise. This is the true story of how science took on the mob. It's 1975, and Doyne Farmer has a problem. He's studying theoretical physics at UC Santa Cruz, diving deep into chaos theory and dynamical systems. But there's this nagging thought he can't shake. Roulette shouldn't be random. The wheel spins at a measurable velocity. The ball has mass and friction. Everything follows predictable physics, which means everything should be calculable. Most people would dismiss this as academic daydreaming. Doyne doesn't. He pulls his friend Norman Packard aside one afternoon. Norman's equally obsessed with physics, equally broke, and equally willing to entertain wild ideas. Doyne lays it out. If they can measure the wheel's rotation speed and the ball's initial velocity, they should be able to predict where it lands, not with perfect accuracy, but enough to shift the odds. Norman's first reaction? Skepticism. Casinos have existed for centuries, but Doyne walks him through the math, scribbling equations on napkins in the campus cafeteria. The variables are all there. The physics is sound. It would take serious work, absolutely. But nothing about it violates the laws of nature. After weeks of late-night discussions, Norman's in, not just because of the money, although that's appealing. They're both children of the counterculture movement, believers in communal living and rejecting corporate America. What better way to fund their idealistic future than by beating the capitalist gambling machine at its own game? They start with research. Vegas casinos use standardized BC Wills regulation roulette wheels, which is perfect because consistency means predictability. The American roulette wheel has 38 pockets, numbers 1 through 36, plus 0 and double 0. The house edge sits at 5.26%, which sounds small until you realize it guarantees the casino wins over time. But what if you could flip that edge? Their first mission is data collection. They need to understand how real casino wheels behave, not theoretical ones. So they make a trip to Vegas wearing baggy long-sleeve shirts, looking like exactly what they are. Hidden under Doyne's sleeve is a small cassette recorder strapped to his wrist. The plan is beautifully simple. Every time a reference point on the wheel passes a fixed spot in the room, Doyne taps the recorder's button. The wheel completes another rotation. He does the same tracking the ball. Later, they can analyze the timing between clicks to calculate velocities and deceleration rates. In practice, awkward as hell. Doyne's sweating through his shirt trying to tap subtly while pretending to be a casual gambler. Norman's nearby taking mental notes on everything. How croupiers spin, how other players bet, how pit bosses watch the tables. They're gathering intelligence on an enemy they barely understand. They leave Vegas that first trip with no winnings, but something more valuable. Data, hours of recorded clicks representing wheel rotations and ball speeds. Back at Santa Cruz, they spend weeks analyzing the patterns, and patterns emerge. The relationship between where the ball leaves the track and where it lands isn't random at all. With enough measurements, they can identify a 5-number section with significantly higher probability than chance would suggest. 5 numbers out of 38. If they're right, they've just given themselves a massive statistical advantage. But they need to test this properly, which means getting their hands on an actual BC Wills wheel. Doyne contacts Paulson Gaming Devices, the manufacturer. It costs a fortune they don't have, funded by borrowed money and optimism. Then the Port of Oakland flags the shipment. Doyne gets a call. There's a problem with his package. He needs to come down immediately. He makes the 3-hour drive with his stomach in knots, and his worst fears are confirmed when he arrives. 2 FBI agents standing next to his crate. Arms crossed, questions ready. Why are you importing casino equipment? What's your intended use? Are you aware of interstate gambling laws? Doyne's mind races. He can't tell them the truth. He stammers through an explanation about it being a collector's item, a piece of Americana, purely decorative. The agents are suspicious, but apparently not suspicious enough. After 2 hours of interrogation, they let him go. He drives back to Santa Cruz with a regulation roulette wheel in his trunk, heart still pounding. They set it up in Doyne's dorm room immediately. Norman helps construct what they'll later call the eudaimonic guillotine, a tower of metal poles and wires looming over the wheel. A camera mounted at the top photographs the exact moment the ball drops from the track, triggered by a microphone detecting the sound. An oscilloscope tracks motion. Everything's connected, calibrated, measured. It looks like a mad scientist's fever dream, which isn't far from the truth. They run thousands of test spins, photographing and recording each one. The data confirms what their Vegas recording suggested. Roulette is absolutely predictable if you have accurate inputs. The wheel's position, the rotor speed, the ball's location, the ball's velocity. 4 variables, all measurable. Now comes the hard part. They need to measure these variables in real time in an actual casino while surrounded by security and suspicious dealers. And they need to do it fast enough to place bets before the ball stops spinning. The solution is a computer, but not just any computer. This is 1975. Personal computers don't exist yet. The Altair 8800, the machine that will inspire Steve Jobs and Bill Gates, won't even hit the market until next year. What Doyne and Norman need is something that doesn't exist. A wearable computer, small enough to hide under clothing, powerful enough to run complex physics calculations in real time, and reliable enough to work in the chaos of a casino floor. Doyne teaches himself digital electronics from scratch. He's already a decent programmer, but hardware is different. He starts with basic circuits, learning how transistors and logic gates work. Then microprocessors. Then custom circuit board design. He's essentially inventing wearable computing years before anyone else will attempt it. The first prototype is laughably bulky. A circuit board the size of a hardcover book, battery pack, wires everywhere. No way to hide this under normal clothing. Back to the drawing board. Version 2 is smaller but overheats within minutes. Version 3 shorts out when Doyne sweats, which he will absolutely do under pressure in a casino. Norman works on the input method. They need a way to signal the computer that's completely invisible to casino surveillance. After dozens of failed experiments, they settle on something brilliantly simple. Tap your toe twice, the computer registers wheel position. Tap again, it logs ball position. It sounds easy until you try doing it accurately while sitting at a roulette table pretending to be a casual gambler. They practice for hours, days, weeks. Doyne paces around his apartment, tapping inputs with his toes until his roommates think he's lost his mind. Maybe he has. The output system is even trickier. How does the computer tell you where to bet without anyone noticing? They experiment with tiny earpieces, too obvious, vibrating motors, too unreliable. Then Doyne remembers something from a psychology experiment on campus. Small solenoids that deliver mild electric pulses to the skin. They're designed for sensory research, but they might work here. He tapes one to his chest and runs tests. The computer can signal different betting zones by varying the pulse pattern. 3 quick pulses means bet on section 1. 2 long pulses means section 2. It's uncomfortable, occasionally painful, but it works. And it's completely invisible. By late 1977, they have a working system. The computer itself is strapped to the bettor's torso, hidden under a baggy shirt. A battery pack under one armpit powers everything. The whole setup weighs about 5 pounds and makes the wearer look slightly lumpy, but not suspiciously so. Probably, they need to test it for real. Doyne volunteers to be the first guinea pig. On a cold December afternoon, he walks into a small Las Vegas casino wearing their entire apparatus under his clothes. His heart is hammering. The computer feels enormous against his chest, though logically, he knows it's well hidden. He sits at a roulette table and buys in for $50, small stakes. This is just a test. The dealer spins the wheel. Doyne tracks it with his toe switches. Click, click. The ball launches. Click, click, click. He's sweating already, partly from nerves, partly because the equipment generates heat against his skin. The computer processes the inputs and pulses a response against his chest. 3 quick shocks. Section 1. He places bets across numbers 4, 17, 19, 21, and 32. Not adjacent on the layout, but clustered on the actual wheel. The ball bounces, settles. 19. He wins. The The payout isn't huge, but that's not the point. The system worked. From data input to calculation to output to bet placement, everything functioned exactly as designed. He plays for another hour, keeping stakes low, testing the system's consistency. He's up about $200 when he notices something concerning. A man in a cheap suit standing near the bar, watching him. Casino security probably, or maybe just paranoia. Then the solenoid starts misbehaving. His sweat is conducting electricity, amplifying the pulses. What should be mild signals become painful shocks. He needs to adjust the device, but he can't do it at the table. He excuses himself to the restroom. The suit follows him. Doyne locks himself in a stall, heart pounding. He'll need to solve this problem before scaling up. Outside the stall, he hears the crackle of a radio. The security guard is right there, just feet away. Then another voice on the radio calls the guard to a different part of the casino. Some other emergency. The guard leaves. Doyne waits 2 full minutes in silence before emerging. He cashes out immediately and walks straight to his car. Later, back at the motel, Norman is grinning. The test was successful despite the close call. They have proof of concept. The system gives them approximately a 20% edge over the house. In gambling terms, that's astronomical. But they need more people. 2-person teams would work better. 1 person wearing the computer and collecting data, another placing the bets. It splits the cognitive load and makes the betting patterns look more natural. Plus, if casino security pulls the bettor aside for questioning, the person wearing the computer can slip away unnoticed. They start recruiting. Within weeks, they've brought 20 science students into the fold. The pitch is compelling. Use physics to beat the casino, split the profits equally, and fund an experimental commune where they can pursue research free from corporate or government constraints. It's 1978. This kind of idealism still sounds plausible. They call themselves eudaimonic enterprises. The name comes from Aristotle's concept of human flourishing. Their goal isn't just money, it's liberation through applied science. At least that's what they tell themselves. The initial investment has reached $10,000, drained mostly into equipment and failed prototypes. They don't have capital for a sustained campaign, so the strategy is conservative. Start with small bets, build the bankroll gradually, then scale up as the funds grow. But there's still the question everyone keeps asking: what happens if we get caught? Norman's answer is reassuring. The computer only predicts a 5-number sector, not a specific number, so they'll spread bets across the table. To casino observers, the pattern will look random because the numbers aren't adjacent on the layout. They're only clustered on the physical wheel, which the pit boss isn't tracking. Plus, technically, using physics to predict outcomes isn't illegal. It's just math. They're not manipulating the wheel or bribing dealers. They're simply thinking faster than everyone else. The group seems convinced. After all, casinos make obscene profits. Why not redistribute some of that wealth to people who will actually do something meaningful with it? They spend the spring of 1978 in intense preparation, building more computers, training team members, running simulation after simulation. Everyone needs to operate the equipment without thinking, make it second nature. The toe taps must be precise. The solenoid signals must be interpreted instantly. There's no room for hesitation. Norman thinks they're rushing. The equipment still has reliability issues, but Doyne won't slow down. They're so close. August 1978. 16 baby-faced physics students arrive in Las Vegas with hidden computers strapped to their bodies. They split into 8 teams, 2 people each. The plan is to hit multiple casinos simultaneously. The Horseshoe, the Silver Nugget, the Golden Gate, Harrah's. Doyne and his partner head to Harrah's. Norman takes his team to the Silver Nugget. As they step under the casino lights, there's a strange mixture of confidence and terror. They've prepared for months. Now it's real. The bets start small, $2, then $5, then $7. Data collection, calculation, bet placement. The rhythm takes hold. Within the first hour, Doyne's team is up $1,200. Adjusted for inflation, that's about $7,000 today. Not bad for an evening's work. The other teams scattered across Vegas are doing similar business. Everything is working. until casino security starts paying attention. These young hippies with their awkward betting patterns and nervous energy don't exactly blend in with the regular clientele. Pit bosses begin lingering nearby, watching closely. After several hours, the teams regroup at a motel. The mood is tense. Several people report uncomfortable encounters with casino staff. One woman's solenoid malfunctioned so badly it burned her skin. There's blood on her blouse. Multiple computers failed mid-session. Broken wires, short circuits, dead batteries. The technology is primitive and fragile. Norman blames Doyne for pushing too fast. Doyne can only think about what might have been. If all 8 teams had scaled up to $50 bets, they'd be sitting on $250,000 by now. The risks suddenly seem more justified. They huddle in a parking lot under fluorescent lights, counting crumpled bills. The final tally is $10,000 profit. Not nothing, but not the fortune they'd imagined. And it came at significant cost: equipment damage, minor injuries, near confrontations with security, and serious fractures in group morale. They face a choice: reinvest everything, build better equipment, and return for another run, or take the money, split it evenly, and walk away while they're still ahead. After hours of debate, they choose the latter. Friendship and safety matter more than the fantasy of millions. The group dissolves. Most members return to their academic careers, but Doyne Farmer and Norman Packard don't abandon the work. They continue refining the system privately for several more years, making occasional trips to Vegas and Reno. The equipment improves. The burns stop happening. They get better at blending in. They never strike it rich, but they prove the concept beyond doubt. Roulette is beatable with physics and computation. Decades later, in 2012, Doyne finally revealed the full story publicly. He'd kept quiet for years, not wanting to help casinos defend against the technique. But by then, casino technology had evolved. Sophisticated surveillance systems and rapid wheel changes made their method obsolete. His final statement on the matter was characteristically defiant. "I kept it silent because I didn't want to communicate any information that might prevent anyone from taking the casino's money." The computers they built are now museum pieces, primitive relics of an analog age, but the principle remains. Doyne went on to become a professor and complexity theorist. Norman Packard co-founded the Santa Fe Institute. Both achieved the scientific recognition they'd sought. Their Vegas adventure wasn't really about gambling. It was about proving that intelligence and determination could crack systems everyone assumed were unbeatable. The house always wins, they say, except when it doesn't. Except when a couple of physics students decide the rules don't apply to them and spend years proving it. The money was never the point. It was about the audacity of the attempt itself. The equipment they built sits in museums now. Curious artifacts from when wearable computing meant batteries taped to your ribs and wires running down your pants. But the real legacy isn't the hardware. It's the proof that systems designed to be unbeatable aren't, if you're willing to think differently enough and work hard enough to be right.